Okay, let's extend our relative motion ideas to acceleration. So let's look at a link again, and this link has not only an omega now, but we also have an alpha. And of course, this alpha can be in a different direction than our omega. It can be, if omega is clockwise, we could have a counterclockwise alpha, which means we'd have deceleration occurring in our angular acceleration. Okay, so this leads to an acceleration of b. Let's just draw it in this direction. And an acceleration of a, like we've seen before with velocity, only now we're dealing with accelerations. So let's draw this deconstruction that we have been doing now for these. So this leads to an acceleration. Oh, let's use a line to make this look nicer. So this leads to an acceleration here where we have a translation. Let's say acceleration of A is our translation. And then we'll add to that. So this isn't like the addition here. This is an equal sign. We'll add to this the acceleration due to rotation. And we'll take as our base point, again, A. And as we accelerate, we will end up with an acceleration due to rotation. I'm going to draw this in red. So I'll call this acceleration of B with respect to A, which also is this. We can take a position vector here again, which is, oops, let's get this labeled, which is a position vector of B with respect to A, drawn from a fixed point. And I don't mean that A is fixed, I mean that there's some fixed point over here somewhere, and we'll have a R, A, and an RB, and already I see an issue. Okay, I clean that up a little bit. So you have a position vector from some fixed point with a fixed reference frame of RA and RB, and then you get the RB with respect to A. So we have our acceleration of B with respect to A, and that's actually has components of our acceleration of B with respect to A, tangential, and the acceleration of B with respect to A, normal. And I've got these backwards. It's one of those days. This is the normal, and this is the tangential, obviously. So those are the components of this acceleration that we end up with. So how do we construct that? Well, we construct it from the velocity. Velocity of B equals the velocity of A, our relative velocity approach, and the velocity of B with respect to A. And what we do here is we take the derivative of these and voila, we have acceleration. So we end up with the translation component and the rotation component, just as we did in velocity. So again, this is acceleration of B equals the acceleration of A, point A, plus the rotational, which we can break up again into the acceleration of B with respect to A tangential, plus the acceleration of B with respect to A normal. So our acceleration of B vector equals an acceleration of A plus an acceleration of B with respect to A. And this, again, can be broken down into two components, a tangential and a normal component. So this is acceleration of B with respect to A tangential and the acceleration of B with respect to A normal. So of course we can take this idea here and generalize it like we always do and say that the acceleration of B equals the acceleration of A plus alpha cross R of B with respect to A minus omega squared R of B with respect to A. And so all we need to find is the position vector of the link of B with respect to A here. So we just need to find this from a fixed point and then just cross that with, well, we take alpha and we cross that position vector. And then we just multiply omega squared times R of B with respect to A. For this is for planar. This is a planar analysis. So we can simplify this. Recall that in the 3D we had omega cross R essentially. So let's do an example. So we have this slider with two links connected to a fixed point down here at A, and this is the geometry of the situation. In addition to all this, we have the angular velocity of BC, or CB, however you want to do it, is 2.43. Let's go this way. And the angular velocity of BA and the angular acceleration of BA are both given. And this is in this direction, in this direction. So this is 10 and this is 20. So these are in rads. So this will be rad per second. And this will be rad per second squared. These are in feet. Let's imagine an X and a Y direction. Then our task is to find the acceleration of C at the instant shown. Okay, acceleration of C, piece of cake. We'll just use our relationship from above. The acceleration of C equals the acceleration of B plus some alpha cross R C to B. Let's not forget this portion, minus omega squared r c to b. Omega squared is a scalar here. So let's look at what we got. Take a step back, look at our problem. Okay, well, we can easily determine these. We have the geometry of the situation, so that's pretty simple to do. We're also given this and this. So these would be BC here. And actually, we're not given this. And this is BC. So we need to find acceleration of B and alpha somehow. So we got a lot of information associated with BA here. Let's look at BA and see what we can do. It's just rotation about an actual fixed point, fixed to the reference frame. So we could do an acceleration of B down here equals minus 20k. Well, let's write out the formula first. Equals the acceleration of A, which is 0, plus alpha cross r plus omega squared cross r. And this r is going to be the r of B with respect to A and B with respect to A here. So now we look at this and we see that all these are easily calculatable. And this is given, and this is given. So we could find the acceleration of B that we need for our equation up above. So acceleration of B equals minus 20 from here, k, cross let's go minus 0.25 sine of 45 degrees I for our R plus 0.25 cosine of 45 degrees J minus 10 rads per second squared times the same thing. So, as these problems typically are, this is just cookbook plug and chug numbers. So, the acceleration of A equals, essentially you're going to end up with a 21.24 I component minus a 14.16 J component. Acceleration of B. Okay, therefore, our acceleration of C is going to be this acceleration of B we just calculated, plus, again, our alpha K cross our C with respect to B this time, minus omega squared times our C with respect to B. And let's get our vectors marked here. So this equals the acceleration of B plus, so let's write this little, I'll write out RC with respect to B. Now remember, you can take your position vector actually from A, since A is a fixed point. And there we go. So this equals, and I'm just writing alpha, or the acceleration of B here, because we know it's going to be this. And there just isn't enough room for everything. Plus, let's do this cross product here. And it's going to be alpha BC times 0.17, and that will be K crossed I, which is J. Finishing out the rest of these calculations above gives us those values. And so then we can look at our I's and our J's. We know that AC we can write as the component in the J direction. So here are our two equations we develop. And so then alpha equals, so here we go. Our acceleration at c is 13.5 down in the opposite direction, and alpha equals 27.7.